Hello, my name is Clayton. I'm one of the tutors at the Natural Sciences Tutoring Center here at SCC. Today I will be covering resonance, which is really just a continuation of Lewis structures, which was the previous video. All right, let's go ahead and jump into it here. Resonance is the delocalization of pi electrons. Pi electrons may be found either in pi bonds or in lone pairs. Because we're only concerned with pi electrons, the sigma structure of the molecule will remain unchanged, which means we should not be breaking any sigma bonds. So if you're breaking sigma bonds in an effort to show resonance, it is incorrect. In general chemistry, we ran into resonance whenever a pi bond could reasonably be formed between any of multiple atoms, and when it was seemingly arbitrary which atom was selected. So let's go right to a couple examples to make more sense of this. If we consider the polyatomic anions carbonate, nitrate, and phosphate, we would get the following Lewis structures, again based on the previous principles from the last video. Okay, so let's zero in on carbonate first. This pi bond right here between carbon and this particular oxygen could also have gone to either of the other two oxygen as well. So why did I choose the top oxygen in the structure? Well, the reason I personally chose to put the pi bond between carbon and that top oxygen is because I like symmetry. And I think it looks better than if I were to put it on one of the side ones, because that would throw the whole thing off. So clearly this is an arbitrary reason for why I placed the pi bond exactly where I placed it. It could easily have gone to either of those other two oxygens. If we look at nitrate and phosphate, we would see similar patterns. In general chemistry, this is typically the extent to which we studied resonance. Now the question is, which of these Lewis structures is correct, or are all three correct? The answer to this question is a little more complicated than a simple yes or no, or by merely selecting a single structure. Resonance structures serve as a representation of how the electrons are distributed among the atoms in a molecule. The structures drawn here, if we go back to carbonate, are all correct, but none of them truly represent what carbonate actually looks like. So we're in this weird middle ground. Yes, each one of those is a representation of carbonate, but none of them reflects reality. These three structures are more for us as humans to help us visualize where the electron densities lie. The reality is that carbonate is actually a combination of all three of these resonance structures. If we were to take any one of these structures at face value, then we would expect the double bond to be shorter and therefore stronger than the single bonds. Experimental data suggests, however, that all three of the carbon-oxygen bonds are of equal strength. We can therefore conclude that the electrons within this pi bond are actually distributed equally between all three carbon-oxygen bonds. This shows us that although none of the resonance structures of carbonate are exactly accurate, if we imagine them to be overlain upon each other, we can get a decent picture of what the true structure actually looks like. Therefore, we could ascertain that the strength of each of these carbon-oxygen bonds lies somewhere between a single and a double bond, and its length must therefore also be shorter than a single bond and longer than a double bond. If we go ahead and look at carbonate one more time, all three of these resonance structures are of equal stability, so they're all considered equivalent. In organic chemistry, we will be moving forward into non-equivalent resonance forms. Let's look at acetone for a quick example of this. Here we have a carbon-oxygen double bond, but through resonance, I could take the pi electrons in this bond and move them onto the oxygen. I could localize them onto that oxygen. Here now we have a separation of charge, so we have a positive formal charge for the carbon and a negative formal charge on the oxygen. This is clearly less stable than if we simply had that pi bond on there, but it is technically a possible resonance form of this compound. So that's kind of the direction that we are heading in organic chemistry. So I just want to prepare for evaluating resonance forms rather than just acknowledging that they exist. Okay, well I think that pretty much covers resonance in general here. I will have another video linked that has practice problems involving resonance, so look out for that. This is the third video in a series of videos that are designed to shift our mindset from a general chemistry understanding to an organic chemistry understanding. So also just keep a lookout for the following videos. The next one should be linked here at the very end of this video. All right, thanks again. My name is Clayton. See ya.